Hello everyone! Today we will look at the moment of inertia. If you recall, last time we used the moment of inertia for our analysis of the motion of the turntable. However, it was more or less a given quantity, but today we will look into how we can measure the moment of inertia. Our apparatus consists of an assembly of two discs. On the smaller disc, we wind up a thread. The other end of the thread runs across a pulley, and there's a weight attached. When we let go, the weight sinks to the floor, and the taut thread sets the disc into a spinning motion. Note the white marker tab, which helps us to follow the motion of the thread when we do video analysis. To analyze the motion, we assume that friction is negligible. In that case, the sum of all potential and kinetic energies must remain constant. What are those energies? Well, we have the rotational energy of the disk, 1/2 times I times omega squared. We have the linear or translational kinetic energy of the driving mass, 1/2 times little m times v squared. And that driving mass also has a potential energy, negative mgy. In this case, we count y as positive in the downward direction, so y increases as the mass sinks to the floor. The linear speed of the driving mass, v, and the angular speed of the spinning disk are related via omega equals v over r. So now we can use conservation of energy. E initial equals E final. Initially, we have no mechanical energy because nothing is moving, so all kinetic energies are zero, and we also choose the initial potential energy to be zero. Sometime later, when the mass has traveled a distance y, we do have both rotational and linear kinetic energy, and we also have a now lower potential energy. So we add the three terms, 1, 2, and 3. We replace the angular velocity with the linear velocity divided by r. We also note that as the mass sinks by a distance y, our marker tab moves the same distance x in the horizontal direction, so x equals y. Solving for v, we get a relationship between the velocity and the travel distance x. Now this equation looks very similar to one of the kinematic equations you learned early on in the semester, namely v squared equals 2ax. The acceleration must hence be equal to this expression in square brackets. We now solve this expression for the moment of inertia, and we have an experimental way to determine I. All we have to do is measure the acceleration via video analysis.